Welcome back to Mustang Physics. Today we want to talk to you about damping and resonance. So let's start here. Damping, that happens when there's a frictional force within simple harmonic motion. So, we tend to overgeneralize friction as bad, but friction can be really good. So if you're playing piano and you want a note to play, but then you want that note to stop, you need something to damp the oscillation of the string. A string, remember, acts as a simple harmonic oscillator. So if you open up a piano, you'll see these little felt wedges, and there's actually a pedal that will lift all those felt wedges off, or they'll let them rest on the string after you release one of the keys so that the note ends when you lift up your finger, or if you hold down that pedal, the note will continue and the string will continue to ring even after you've let it off. Now, one of the most important things to damp is the oscillation that can happen within a car's suspension. So let's shrink this down just a little bit and just leave it off to the side. And let's think about this graph here. This shows that the oscillation of a simple harmonic oscillator, its amplitude decreases as an exponential function with time. Now, there's a lot of math on this website, and I'm not suggesting that you go into this. This is Hyperphysics, by the way. Great website. It's basically got all of physics organized, run by Georgia State University. Highly recommend it. So you can see that there's several lines on here. If you don't have much damping, you can see that oscillation will continue for quite a while, and the amount of amplitude with each successive bounce decreases in an exponential decay. And if you have what we call critical damping, let's go to that critical damping. That's this red line here. You don't get a bounce. You just go ease back to the equilibrium position. So critical damping is sometimes a little bit more damped than what a car would be. A car's suspension, if we take a look at that, typically has springs to actually suspend the weight. And then this introduces friction. It's the shock absorber. The shock absorber adds that damping so that when you hit a bump, your car doesn't continue to bounce and bounce and bounce and bounce. There's lots of different designs of this. Sometimes the shock is inside of the spring. So you can call that, it's a coil-over shock. Sometimes it's a strut. There's lots of different suspension designs, but the idea is there's typically a spring that actually holds the weight, and then there's a shock absorber that adds friction so that your car doesn't act as a simple harmonic oscillator, and at least it doesn't act as an undamped one. So if you have too much damping, it can add so much friction that it takes a long time for the oscillator to get back to its equilibrium position. And we don't want that to be happening inside of a car suspension, because then you hit a bump and your car rides low or rides high for a long time as the suspension comes back to its normal height. So let's take a look at what this looks like within a FET simulator. So I've got FET masses and springs here, and we can hang a mass, and we'll go to slow so that we can kind of watch this a little bit more easily. And we'll zero out the thermal energy here. If there's no damping, what we see is if we show the equilibrium and the natural length of the spring, we can always see the displacement of the spring's end from where it started. If we drag the mass and stretch the spring, we've added a lot of elastic energy. And if we release it, of course, we get simple harmonic motion. Now, as we get that simple harmonic motion, you'll notice that we're not having any thermal energy generated. In other words, this oscillator would go back and forth and back and forth at the same amplitude over and over and over and over without end. Well, of course, in the real world, there is a loss to energy to the surroundings. And one of the losses is actually even within the internal friction of the spring itself. So if we add a little bit of damping, this becomes a little bit more real world, and you can see that there's a gain in thermal energy each time that the mass is moving because the spring is having to stretch. Now, we could add to that damping, it could be lots, if we put a shock absorber on this, something to resist movement in any direction, not just towards the center. So notice that when we move the damping to lots, we go right back to the equilibrium pretty quickly, and all of the energy that we added when we displaced the mass has now all turned into thermal energy. So that's what damping represents in a simple harmonic oscillator. Now, there's one more phenomenon in the notes besides damping that we want to talk to you about today, and that's forced resonance. So we're looking at this slide here. So forced resonance, you can see that there's a graph here where the amplitude of a simple harmonic oscillator really spikes. In fact, it goes off the chart. And that's if energy is pulsed in at the same frequency that the mass would typically vibrate at. So if we were to take a simple harmonic oscillator and displace it and let it start oscillating back and forth, if we gave it a little push every time it did that, at just the right moment, we'd be able to push it just a little bit further and the amplitude would get bigger and bigger and bigger. So, a pendulum acts like a simple harmonic oscillator. You might have done this on a playground at one point or another with a friend when you push them on the swings at just the right moment. That forced resonance means that you're adding energy at just the right moment to help the oscillator have a larger amplitude. Now, this can often happen kind of unintentionally when one thing is vibrating and another at another thing's natural harmonic frequency, and that will cause that second object to start vibrating a lot. So if you maybe in your car, if you drive at a certain speed or if you drive on a certain road and all of a sudden your car gets really buzzy or some part just starts vibrating, it might be in forced resonance where something else is also vibrating at that frequency and it's causing that second object to buzz or vibrate because it's at its natural resonant frequency. So let's show you an example of that. We've got a mass here, mass 1, and it's attached to a driver. That driver can move up and down. If we turn on this driver below here, now it's set to 1 hertz. Now, with this amount of mass, 2.533 kilograms, and a spring constant of 100 newtons per meter, that if we do the calculation to find the natural resonant frequency of this oscillation, what we find is it's 1 hertz. So if we get this to be still, there we go, maybe. And there we go. And we turn the driver on, what we see is even though the driver's not really putting in much energy with each pulse, that the amplitude of the oscillator really grows, and it'll grow to a maximum that's quite large. Of course, there is some reasonable extension that beyond which it can't go because the spring just can't get that long. So we have a really high amplitude now because the mass is in forced resonance. Notice that if we change the frequency of the driver just a little bit, then the pulsed energy that is input into the simple harmonic oscillator isn't at just the right time, and so it doesn't build on itself. Now, as we get closer and closer to the correct frequency, we see that we do get some growth in amplitude. And back to the notes here, that's why we see these lines that are in blue and green, where there's some increase in amplitude when the frequency of the pulses input to the simple harmonic oscillator are close, but not quite the same frequency as the simple harmonic oscillator would have if it were just simply disturbed and allowed to vibrate typically on its own. So when we get those really close, right, the natural harmonic frequency is 1 hertz, and I'm pulsing it at 1.01 hertz. It looks almost like it does when they match. This is an interesting simulation. If you have Flash, you can run it. You can actually have more than one resonator. And if we take a look at some of the different ones, like here's number 2, it's got more mass and a stiffer spring, so it vibrates at 1.5 hertz if we're to disturb it. And then resonator 3 has less mass and an even stiffer spring. It oscillates at 2 hertz if we disturb it. And that allows us to see if you had something like your car that's made of a lot of different parts, each object has some natural resonant frequency. If the sound that your engine is making or some other part of your car or the tires as they roll along the pavement are making a sound at a particular frequency, and that frequency doesn't match the resonant frequency of any of the parts of your car that could oscillate, then they don't vibrate all that much. It's just the normal background hum of your car. But as that frequency gets really, really close to one of the resonant frequencies of the resonators here, you can see that resonator 2, which on its own, if you just plucked it once, would oscillate at 1.5 hertz. All of a sudden, its amplitude is really big because it's being agitated at a frequency where it naturally vibrates or oscillates anyway. So, if you've heard kind of that buzzing in your car, that's what's happening is at that particular speed, at that particular engine speed, that's agitating some part of your car that's oscillating. And of course, if you pulse in energy at a slightly different frequency, that effect starts to go away as that frequency gets closer and closer and closer to the natural harmonic frequency of another resonator, then it goes into forced resonance. So a really famous example of this is a opera singer singing at a particular note that resonates with a glass, being able to break that glass. And you find if you search the YouTube, you'll find some videos of people doing precisely that. The glass under high speed video is pretty interesting to watch. It doesn't capture well in motion capture, otherwise I'd show it to you. But I certainly recommend that you go find a video like that. All right, thanks for watching. Hopefully that helps you with what damping and forced resonance are within simple harmonic oscillators. We'll see you next time.